Okay, so our problem says that at 10 degrees Celsius, 8.9 times 10 to the negative 5th grams of silver chloride will dissolve in 100 milliliters of water. And the first part is to write the equation for the dissociation. So you just write out sodium chloride, and it breaks apart into the silver ion and the chloride ion. And that's the first part.
Okay, for the second part, we have to calculate the solubility in moles per liters of silver chloride in water. Now, to do that, we take silver chloride, we go through the process of turning it into moles, and then dividing by liters. And once we're done with that, we end up getting 6.2 times 10 to the negative 6 molality of silver chloride. And that's all.
Okay, part A, number 3. Calculate the value of the solubility product constant, KSP, for silver chloride at 10 degrees Celsius. In the last part, we found that we have 6.2 times 10 to the negative 6th molarity of silver chloride. So, and given this equation, probably shouldn't have written that there. Okay, anyways. Okay, so that's that, and then we don't have any silver and we don't have any chloride ions. And we're going to make an ice table. So we know that silver chloride is going to dissociate completely. So we would lose everything, minus 6.2 times 10 to the negative 6. And they have an equal mole ratio, so you would just add that amount to the product side. And now you have 6.2 times 10 to the negative 6. Okay, and the equilibrium equation, KSP, is the silver times the chlorine. You don't include the silver chloride because it's a solid. And we know the concentrations of that is 6.2 times 10 to the negative 6 times 6.2 times 10 to the negative 6. And that gives you 3.84 times 10 to the negative 11. That's the answer.
Okay, so for part B of this problem, it says that at 25 degrees Celsius, the value of KSP for the lead chloride is 1.6 times 10 to the negative 5th, and KSP for silver chloride is 1.8 times 10 to the negative 10th. And for the first part, it says you have 60 milliliters of 0.0400 molarity sodium chloride is added to 60 milliliters of 0.0300 molarity lead nitrate, and they want to know if a precipitate will form. So to know if a precipitate will form, you have to find Q and then compare it to the KSP that they gave you here. So first, you start off with the sodium chloride and the lead nitrate.
Okay, and then for B, we need to calculate the concentration in moles over liters of Ag and a standard solution of Ag.
They give you this information, and you change the milliliters into liters.
Okay, so Ag.
Okay, and then it tells you that volumes are additive, so that's kind of a hint that you're going to need to add those two volumes. And you get liters. And then the equation that you're working with is this, the dissociation of lead chloride, and breaks apart into the ions. balance, and then you find what the KSP, what the equilibrium expression is, because then that's how you're going to find Q. KSP concentration this ion squared because of the coefficient. And then from there, you have to do the dilution problem for each compound. So,
But you have to read it wrong.
so you plug in the original information they gave you.
You have to read it. Okay, ready? This is group E.
And you're looking for M2. And the new volume is the 12,1200 liters.
Okay, this is group E.
And then when you solve for that, you get O2 equals M2. And then if you do this one, you have times the new volume, and then you get this value for M2. And then you can use this KSP expression to find Q. And you have to square
And for B, calculate the concentration in moles
this
of
one
Ag in a standard solution
because
of AgCl4 and
it's the one that has to do with this part of the problem, and the coefficient was 2. And then this one.
And since we don't know what the concentrations are for Ag or ClO4,
And then when you solve for that, you get Q equals 6.00 times 10 to the negative 6. And the KSP is given to you, it's this one. So you just compare those and you see that the Q is smaller than the KSP. And that means a precipitate will not form, and
we don't know what the concentration is.
Because it wouldn't be.
no precipitate will form.
I really don't think I did.
And it'll dissolve more. And that's it.
Okay, for B part 2, we have to calculate the equilibrium value of Pb2 plus in 1 liter of saturated PbCl2 in a solution which gives us 0.25 moles of NaCl. Now, that comes out to being PbCl2 decomps into Pb plus 2 plus 2Cl minus. Now, they did give us the 0.25 moles of Cl, but since it's just 1 liter, we can automatically assume this as molarity. Now, they gave us 0.25 molarity of Cl. We can make an ice table out of this, and because this is a solid and the value is so small, we can neglect PbCl2 from the ice table. We have Pb plus 2 and 2Cl minus. Now, our beginning values for PbCl2 are 0.25, or for Cl is 0.25 molarity. And for Pb, we know that this is going to be plus X and plus X2, because they have 2 mole for Cl and a normal, just 1 mole for Pb. Now, those values can be put into a KSP equation, and they gave us our value for KSP. So, we have KSP equals Pb times Cl squared. Given our values, we have that 0.25 molarity plus 2x for Cl minus squared, but the 2x is so negligible we can just keep it from the equation. So we have 0.25 molarity times x equals 1.6 times 10 to the negative fifth. Now, if you take 0.25 squared and then you take the 1.6 times 10 to the negative fifth and you divide it, x ends up being, x is 2.56 times 10 to the negative fourth.
This is part B, number 3. If 0.100 molarity NaCl is added slowly to a beaker containing both 0.120 molarity silver nitrate and 0.150 molarity lead nitrate at 25 degrees Celsius, which will precipitate first, silver chloride or lead chloride? Show calculations to support your answer. So you have, they gave you 0.120 molarity of silver nitrate, and they gave you 0.150 molarity of lead nitrate. These are two different equations, and they gave you two different equilibrium values. So the first equation for the silver chloride, it's like this. And then the other one, lead chloride. Okay, so those are the two different equations that you're going to be working with, and you're trying to compare the molarity of chlorine ions for both of them. So you make an ice table. So first, all you have is 0, you have the 0.120 molarity of this, and you don't know the values of these. And then here, you don't know you have 0.150 molarity. And then this will come out to be x. The x is insignificant here because the sig figs will just make it 0.150 in the end. Okay, so now you're given the equilibrium concentration, or constant. So you have, which is 1.8 times 10 to the negative 10, which is right here for AgCl, equals the concentration of Ag times the concentration of Cl, which is 0.120 times x. Now you solve for x, and for this one you'll get 1.5 times 10 to the negative 9th molarity, and that's of the Cl minus, that's x. And then this one, it's 1.6 times 10 to the negative 5th, which is given up here, equals the concentration of the lead, which is 0.150 times x, and that's squared because of the coefficient there. And then when you solve for x, you'll get 0.0206 molarity of the Cl minus, because that's also the x. And now you compare these two values, because the chlorine in the silver chlorine formula is a lot smaller than this one. The silver chloride will precipitate first, and that's because the silver chloride will form a precipitate when the chlorine exceeds 1.5 times 10 to the 9th, and it's a smaller value, so it's going to precipitate first. So your answer is that the silver chlorine will precipitate first. Form a precipitate first.